NASA says the artificial radiation belt caused by Operation Argus dissipated by 1961. That gives the impression that there were only 2 radiation belts during the Mercury missions, but the Mercury missions took place before and after Operation Starfish Prime, so there were actually 3 radiation belts during the Mercury missions, and although the artificial radiation belt caused by Operation Starfish Prime was at a higher altitude, there would have been no way of knowing the effect of any energy flux for that whole region. Furthermore, it took until 1982 for levels to drop to half its quantity, and the Apollo missions are said to have taken place between 1969 and 1972. Then, in 2012, NASA says it discovered a 3rd radiation belt surrounding the Earth. Shouldn't it be a 4th radiation belt? NASA claims that although this 3rd radiation belt dissipated months later, they can only speculate as to what caused it. The prevailing theory is that this 3rd radiation belt was most likely caused by a solar particle event, SPE. The question is, if NASA's theory is that the 3rd radiation belt can form during an SPE, then how long would that 3rd radiation belt have been there? 1, 2, 3, or 4 months? Or instead of months, is it years? After all, NASA insinuated that it took 3 years for the artificially formed radiation belt caused by Operation Argus to dissipate. However, as has been established, the artificially formed radiation belt caused by Operation Starfish Prime is still there. This means that all of the Apollo missions would have had to travel through 3 or more radiation belts, the inner Van Allen belt, the outer Van Allen belt, and at least 1 artificial radiation belt formed by Operation Starfish Prime. As pointed out, by the end of the 20th century, levels of radiation in the artificial belt caused by Operation Starfish Prime would have been between 50 to 25 times the already intense background levels for that region of the Van Allen belts. When this artificial radiation belt is factored in, all of the astronauts of the Apollo missions would have had been exposed longer to extremely high levels of radiation than was reported, preventing any safe passage for manned missions through the Van Allen belts regardless of NASA's claims. There have been numerous SPEs over the decades, so the exact number of radiation belts has yet to be determined. The 2012 discovery of a 3rd radiation belt raises an interesting point. NASA speculates that this 3rd radiation belt was formed by an SPE. If NASA is right, then it's reasonable to assume that a radiation belt was formed by the SPE event of August 4, 1972, which was 4 months before the Apollo 17 mission. Also, what about the intensity of this 3rd radiation belt formed by August 4, 1972 SPE? It's already been established that electron fluxes are typically observed at energies greater than 15 MeVs, which exceeds the Apollo spacecraft shielding. And how would NASA have even known about the formation of another radiation belt back in 1972? There's nothing in the literature back then to suggest that NASA even considered the possibility of a radiation belt forming from an SPE, which is a proven fact by NASA's own statement, which is discussed at the end of this chapter. However, it is reasonable to assume that the Apollo 17 would have traveled through 4 radiation belts and have been exposed to radiation longer than any other Apollo missions. As for Operation Starfish Prime, Sir Bernard Lovell called the effects cataclysmic. Solar particle events. Solar particle events, SPEs, can penetrate spacecraft shielding, and the best protection is to avoid them. As we'll learn in this section, SPEs have varying degrees of intensity depending on the source. As SPEs are an evolving science, they are and have always been difficult to predict. As with the Van Allen belts, we encounter a subject rife with discrepancies and conflicting information. Accelerated SPE particles are surrounded by plasma and fields that can produce electromagnetic emissions from microwaves to gamma rays. They can accelerate electrons up to 10 MeV and protons up to and greater than 100 MeV. As quoted by the National Research Council, protons comprise 90% of the energetic ions produced in an SPE, and as mentioned, protons above 30 MeV can penetrate the mid-deck of the space shuttle. This is a very serious situation for any manned mission to be caught in this solar event. Given that SPEs can arrive on Earth within minutes, there would be little to no time for any manned mission to prepare for one. As for preparing for an SPE, the only solution would be to seek the relative safety of LEO, which would put any manned mission below the Van Allen belts and well within Earth's magnetic field, which would offer some protection. But seeking the protection of Earth's magnetic field would require getting there quickly from cislunar space. Given the propulsion systems used in spacecraft during the Apollo era and today, getting there quickly would be an impossible task. Another solution was to turn the CSM around, hoping the service module will take the brunt of the SPE, which was supposed to have been one of the procedures for any encounter. Either way, you have a doomed mission. SPEs are classified as A, B, C, M, and X, with A being the smallest. Solar flares are often associated with magnetic storms, that is, CMEs. The National Oceanic and Atmospheric Administration, NOAA, further classifies these storms into three categories. 1. Geomagnetic storms from G1, G2, G3, G4, and G5. 2. Solar radiation storms from S1, S2, S3, S4, and S5. And 3. Radio disturbances, blackouts from R1, R2, R3, R4, and R5. Each category number means minor, moderate, strong, severe, and extreme, respectively. On January the 20th, 2005, NOAA issued an advisory for a Category 3, a solar radiation storm. This advisory warned that this specific storm had an influx of high-energy protons of greater than 100 MeVs. The advisory went on to say that a rare ground-level event, GLE, was observed. GLEs are an increase of ground-level neutrons and are associated with high-energy protons greater than 500 MeVs. It seems NASA may be holding back information about the August 4, 1972 SPE. Maximum SPE activity during Apollo missions. Bennett and Percy write, "The named Apollo astronauts are, however, a remarkable healthy bunch considering that during 9 alleged trips to the Moon, 1,506 solar flares were recorded, an average of 16.92 per day per mission." J.A. McKinnon, NOAA expert on solar flares, states that 10 to 20% of solar flares could be considered a medium X-ray emitter event and 1%, the deadliest of all, a Class X event. So these astronauts should have encountered 16 to 33 Class M events and at least one Class X event on each mission. As NASA admits, the Apollo missions took place during solar maximum when large SPEs were expected to occur. With the above quote, the National Research Council reiterates the point regarding solar maximum. Either it didn't occur to them that the Apollo missions were in potential danger outside of the protective shielding of Earth's magnetic field, or they mentioned it without explaining, hoping people would not question the insanity of such a momentous decision sending manned missions beyond LEO. The National Research Council. The problem is serious. Over the past 20 years, radiation effects have caused between 1 and 2 satellites per year, on average, to suffer a total or partial mission loss. Satellites at low altitudes in Earth orbit, LEO, stay relatively safe by ducking the intense part of the radiation belts higher up. But at higher altitudes and higher altitudes, where Earth's radiation belts reside and radiation from solar storms invades, radiation hazards cannot be ignored. The above quote also applies to satellites owned by corporations who don't even bother to report problems after an SPE, since there's no regulation that says they have to do so. Hence, the real number of satellites that are affected by solar storms, aka SPEs, is obviously higher. There are people who will point out that there are very few interruptions in communications and internet services, inferring that satellites function well regardless of SPEs. However, it should be noted that communications and internet services are primarily facilitated by underground and underwater fiber optic cables. The National Research Council. It delivered a total dose of radiation over half a day that, had it missed the middle or hit the Apollo missions at either end, would have caused the crew in the lunar module to suffer acute radiation sickness and, given the uncertainty in the estimate, probably even death. This is regarding the SPE of August 4, 1972, 4 months before Apollo 17. This was the largest solar storm ever recorded in the 20th century. NASA says this storm was about 400 rem, yet according to Dr. Percival McCormick, the manager of operational medicine in the Life Sciences Division of NASA, says it would have delivered 960 rems without shielding. If the Apollo astronauts were in the LEM when this had happened, it would have been akin to having little or no radiation shielding, and the command module wouldn't have been much better. As we've established, approximately 0.6 rems is the yearly average dose per person, so with a dose of 960 rems over a short period of time, none of the Apollo astronauts would have survived, or at the very least, they would have been quite incapacitated. The figure of 960 rems is what is mentioned in NASA's reports, and given that we've learned so far, this figure is most likely higher, as SPEs have known to be in the more energetic gigavolt or GeV range. Hence, if any of the Apollo missions had been caught in this SPE, their demise would have been instant. SPEs are unpredictable. SPEs are unpredictable and dangerous to any manned missions outside of the LEO, and experts can't always explain the mechanisms of SPEs, since it is an evolving science, as they themselves admit. Given the unpredictability of SPEs, it stretches credulity that NASA would even take a chance of sending manned missions to the Moon after the solar event of August 4, 1972, which, as previously mentioned, they are supposed to have done with Apollo 17. And that's just one SPE that we've talked about. According to the NOAA, there were 489 SPEs in July of 1969, the same month of the Apollo 11 mission. Also note that in the same year, NOAA or NOAA recorded 7,153 SPEs. The National Research Council, a solar flare and radio burst occurred during the Apollo 12 mission, which had exercised the operational procedures. The National Research Council had an opportunity to explain what Apollo 12's operational procedures were, but failed to do so. In fact, their 3 published reports from 2000 to 2008, there is a total of 1.5 pages of data from the Apollo missions, and at best, that information is scant. Bennett and Percy write, their mission occupied 14.6% of the overall Apollo profile of 89 days, and an average of 268 solar flares recorded during that time was 17.7 of the total number of flares that actually occurred during the Apollo period. Considering the inability of the agency to clad its craft against lethal radiation, and with figures like these, how long could each astronaut actually have spent on the surface of the Moon exposed to lethal radiation is fairly academic. This quote is regarding Apollo 15, which experienced the greater number of SPEs and apparently the greatest avoidance of them. More conflicting information. NASA says that in the event of an SPE, the shielding on the Apollo spacecraft would have attenuated 400 rems to less than 35 rems, and to reiterate, the average yearly dose per person for background and man-made radiation is approximately 0.62 rems. Their contingency for this includes a quick trip back to Earth for medical care, and you'll find that on NASA's website. Given the level of technology regarding rocket propulsion then and now, the fact that the Moon had no atmosphere and no magnetic field to protect it from SPEs, and that it would take 3 days to get back to Earth. NASA needs to redefine what a quick trip back to Earth is. Proponents of the Apollo missions say that 35 rems is safe for short durations, that is, if you believe the shielding capabilities of the Apollo spacecraft. The National Council on Radiation Protection and Measurements, NRCP, says that 35 rems is survivable, but it's obvious, as will be discussed in Chapter 5, that the LM's flimsy design and shielding would not have attenuated 400 rems or 960 rems to acceptable levels for the safety of the astronauts. For the most part, Earth's atmosphere and magnetic field protects us from these harmful rays, but outside of the Earth's magnetic field, there are some of the most penetrating forms of radiation and a hazard to many manned missions. During the 1950s, the only way to detect solar particles within SPEs was through ground-based instruments. These particles were secondary particles called muons, which had reached the instruments on the ground. But for these particles to reach the instruments on the ground, the solar particles within the SPEs had to have exceeded the MeV range with extremely high energies greater than 4 GeV to penetrate Earth's magnetic shield. So, if 30 MeV protons can penetrate the mid-deck of the space shuttle, it doesn't take much to determine what greater than 4 MeV particles can do to astronauts with the level of shielding that the Apollo spacecraft had. A minimum amount of aluminum wouldn't have offered any protection for the Apollo astronauts anywhere outside of LEO. The conflicting information between above quotes of 400 rems and 960 rems for the August 4, 1972 SPE, as well as what would have happened to any of the astronauts if they had been caught in this SPE, is disturbing. Given this conflicting information regarding SPEs and NASA's procedural protocols, the reality is that the Apollo astronauts would most likely have been vaporized. Proponents sneer when you mention the possibility of astronauts being vaporized by an SPE. However, since SPEs can reach into the GeV range, there is no shielding to protect the astronauts with present technology, so astronauts being vaporized is a real possibility. It has been rumored that the Soviets had sent several creatures and a cosmonaut to the moon with their Zond space program in September of 1968. When the craft returned and was retrieved from the ocean, the creatures and cosmonaut were rumored to have been vaporized, and the American government was notified about this. I haven't been able to substantiate it, so for now it'll remain just that, a rumor. But the Soviet Zond space program did exist, and the official record does show that a mission with small creatures on board was sent to the moon and back with seemingly little or no harm to the creatures. In September 1968, they flew an unmanned Zond around the moon, and in November of the same year, another craft loaded with tortoises, flies, and worms took the same trip. Then for once, the Russians hesitated. They wanted more tests. The cosmonauts wanted to go, but they were held back. The Americans might still fail. It was better not to risk all so soon. Tortoises can survive thousands of times the radiation than humans, and rather than err on the side of caution, as the Soviets did by sending an unmanned Apollo spacecraft to circumnavigate the moon, the Americans instead sent the first manned mission, Apollo 8. And it would be interesting to know the real reason the Soviets hesitated. Coronal mass ejections. Coronal mass ejections, or CMEs, are believed to be associated with SPEs and are just as dangerous, though the actual mechanisms of this are still not understood. Coronal mass ejections consist of large balloon-shaped clouds of solar plasma and magnetic field that contain up to 10 to 16th grams of matter and reach speeds in excess of 2,500 kilometers per second. The kinetic energy alone is sufficient to boil the North Atlantic Ocean. CMEs are associated with solar flares and solar energetic particle events and occur most often during sunspot maximum. Most of the energy in such events is associated with CME and not the flare. One doesn't need to be an expert in space physics to know the consequences of being caught in the middle of a CME, which has enough energy to boil the North Atlantic Ocean. To reiterate, the Apollo missions supposedly took place during solar maximum. Proponents of the Apollo missions are quick to point out that SPEs and CMEs are not omnidirectional, thus insinuating the chances of being hit by one is minimal. It is true that SPEs and CMEs are not omnidirectional, but they are reflected by the sun's magnetic field, affecting a much wider area in the solar system, making any manned mission outside of LEO just as vulnerable no matter what area of the sun these emissions emanate from. Therefore, this would have increased the chances of an Apollo mission being hit by an SPE and CME. Although CMEs move slower, they can reach the Earth in approximately 48 hours, so there wouldn't be a lot of time for any manned mission in cislunar space to seek the relative safety of the Earth's magnetic field. Just like CPEs, the prediction of CMEs is difficult. In the 1960s, NASA had several observatories stationed around the world, and as the National Research Council reiterates, prediction of the solar storms is difficult even today, so SPEs and CMEs are a serious risk to any manned mission outside of LEO during solar minimum or maximum years. In other words, prediction of SPEs and CMEs when sending manned missions outside of LEO is far from being an exact science and not something that should be ignored when it comes to the safety of astronauts. Galactic cosmic rays. Now that we've established the hazards of sending manned space missions through the Van Allen belts as well as the dangers of SPEs and CMEs, the Apollo astronauts would also have to have contended with galactic cosmic rays, GCRs. There are two sources for GCRs, radiation that comes from the Sun, called solar energetic particles, and radiation entering our solar system from all directions called galactic cosmic rays. GCRs contain extremely high energy protons, alpha particles, and heavy nuclei. Cosmic rays are measured in MeV and GeV range. They represent about a third of the radiation in space. Although GCRs are always present, cosmic rays from outside the solar system are at a minimum during intense SPE activity from the Sun. As previously mentioned, the Apollo missions took place during that period of intense SPE activity. However, with that intense SPE activity comes solar energetic particles, another form of cosmic rays. Yet, the National Research Council has said that manned missions to Mars will require much more protection and shielding thickness to counter the steady GCR exposure as well as SPEs. A manned mission to Mars will take several months compared to a manned mission to the Moon, which would take 3 to 4 days. However, there's no reason to assume why the same level of protection and shielding shouldn't be applied to manned missions to the Moon, especially during extravehicular activities, EVAs, on the lunar surface, where astronauts have only their zipped-up spacesuits for protection against GCRs, SPEs, and CMEs. Mary Bennett and David Percy write, "These might be technical terms used by experts, but when presented to the general public, there is a potential for the manipulation of reality through vocabulary. The dividing of space into cislunar space, the region of space within the orbit of the Moon, and deep space beyond lunar orbit, lulls the public into false assumptions concerning the safety of manned spacecraft and has little to do with the reality of space environment." When discussing shielding, NASA tends to use terms like cislunar space and deep space, giving the impression that radiation between the Earth and the Moon is more tolerable than between the Moon and Mars, as per the above quote. It's an attempt to differentiate space beyond low Earth orbit, giving the public the impression that the dangers of radiation in cislunar space is minimal compared to deep space, that is, in the case of a manned mission to Mars. There's no difference in intensities with SPEs, CMEs, and GCRs between the areas of the Earth, Moon, and Mars. You would require the same level of shielding for any manned mission, regardless of the duration and distance of the mission. As for the dosimeter readings of the astronauts, NASA has purposely released the average doses that the astronauts received during the mission, but the actual specific dosimeter readings for each astronaut are classified. It has been 50 years since the Apollo mission, so why the secrecy about the Apollo astronauts' dosimeter readings that is needed to be classified, especially considering that NASA has supposedly released the combined average doses the Apollo astronauts received? There can only be two reasons. One is that the readings don't exist, or two, they never went any further than low Earth orbit. It's interesting to note that the average Apollo 11 dosimeter readings are comparable to readings on the International Space Station in low Earth orbit. A quote here, a quote there. Anyone who's read any of the numerous books on radiation in general knows that the two scientists can agree on different effects of radiation on Earth, whether it's natural, background radiation, or man-made. Yet how interesting it is that few scientists who have studied NASA's data on the Van Allen belts, SPEs, CMEs, and GCRs agree on every aspect of them, while other scientists who haven't even been bothered to research it for themselves agree to its validity when reading other scientists' research papers on this. This method of peer-reviewed papers should be approached with caution, given some of the recent disclosures of fraud within the scientific community and the influence of fiduciary obligations. In the previously mentioned article online, Robert A. Bronig went out of his way to try to discredit anyone who questions the Apollo missions by labeling them conspiracy theorists, and then went on to rant about their supposed tactics. Bronig writes, Absent the ability to perform a proper quantitative solution, the conspiracies are forced to look for circumstantial evidence. They can generally do little than point out what they believe to be suspicious activity or resort to quote mining. Quotes are used all the time by people on both sides of the discussion, including Breitling himself, and there's nothing wrong with it. But there's a reason he specifically mentioned the tactic of quote mining, since there are some very interesting quotes made by scientists and professionals themselves when specifically talking about the Apollo missions and related subjects, as these statements more than cast doubt on the validity of these missions. In fact, quotes can actually destroy decades of research. An example of this was recently revealed in the prestigious medical magazine, the Journal of American Medical Association, JAMA, when it disclosed how 3 Harvard scientists were paid approximately $25,000 50 years ago to falsify their research on heart disease. For the last 5 decades, hundreds of thousands of scientists, doctors, and journalists were manipulated into believing a fabricated story. It's disturbing that very few of these professionals questioned the findings of these 3 Harvard scientists. What is even more disturbing is the fact that millions of people around the world who trusted these Harvard scientists were possibly harmed by these trusted professionals. Therefore, thanks to Robert Breitling, we'll close this chapter by showing the importance of quote mining by professionals inadvertently on those purposes. Show how quotes can undo decades of research by challenging established beliefs. Dr. James Van Allen regarding the radiation belts. Our measurements show that the maximum radiation level of 1958 is equivalent to between 10 and 100 Roentgens per hour, depending on the still undetermined proportion of the protons and electrons. Since a human being exposed for 2 days to even 10 Roentgens would have only an even chance of survival, the radiation belts obviously present an obstacle to spaceflight. Unless some practical way can be found to shield space travelers against the effects of the radiation, manned space rockets can best take off through the radiation-free zone over the poles. 10 Roentgens is 9.329664 rems, and 100 Roentgens is 93.296637 rems. As established earlier, the average yearly dose per person for background and man-made radiation in the United States is approximately 0.62 rems. As Breitling will quickly point out, Dr. Van Allen mentions a human being exposed for 2 days, while the Apollo astronauts spent a total of 2 hours traveling the outer region of the outer radiation belt. However, we've learned that NASA doesn't fully understand the radiation belts, and there is evidence of electrons far greater than 15 MeV, which extends the Apollo shielding capabilities. So, 2 hours or less in the radiation belts may well have been enough to have seriously harmed the Apollo astronauts, that is, without even considering the artificial radiation belt formed by Operation Starfish Prime. Further, the Apollo missions apparently spent 15 minutes in the most intense inner-dominated proton belt, which NASA itself says manned missions must avoid. However, as has been established by Gerald White, NASA doesn't know for sure the energy fluxes of these high-energy protons and electrons in both the inner and outer radiation belts. So, 15 minutes in the inner-dominated proton belt may well have been enough on its own to have seriously harmed the Apollo astronauts, given their lack of shielding. As I mentioned earlier, it took over 30 years for Dr. Van Allen to refute his own statement about manned space missions traveling through the radiation-free zone around the North and South Poles. In response to a 1-hour documentary called Conspiracy Theory, Did We Land on the Moon?, shown on Fox TV in February 2001, Dr. Van Allen reportedly said this in an email. However, the outbound and inbound trajectories of the Apollo spacecraft cut through the outer portions of the inner belt, and because of their high speed, spent only about 15 minutes in traversing the region and less than 2 hours in traversing the much less penetrating radiation in the outer radiation belt. The resulting radiation exposure for the round trip was less than 1% of a fatal dosage, a very minor risk among the far greater other risks of such flights. I made such estimates in the early 1960s, and so informed the NASA engineers who were planning the Apollo flights. These estimates are still reliable.